on constant slow order terms. Let me address, which is the other question, couldn't you always choose C big enough to get things to cross? And so let me show you a non-example. Okay, so it's not true that you can always get the curves to cross. Question?
According to that definition, does that mean say that example 1 is also asymptotic?
Sure.
Something like
K plus 1, end of the K plus 2, end of the K plus 2. So what you'd really like to have somebody show you is that an analogous version from the lower bound side too. And that's what I'll end the lecture with, is discussing that. So this only gives you a one-sided bound on what's going on. Okay? So what would be really bad is, you could not just drop lower, if you could actually say it's big O of like n to the k minus 1. Okay, that would be pretty dangerous. If n squared than n, that would start seeming wrong. That would start seeming bad. So let's just verify that that's not the case. K at least 1 not go n to the k minus 1. Okay, so it's just sanity check. All right? So in other words, you really do care about the leading power of n. Okay, it really does matter. Okay? So how would you prove this? I would recommend by contradiction. So you assume that that n to the k is big O of n to the k minus 1, from which you would derive and conclude that the original hypothesis is false. So suppose, for contradiction, so what is this bias? Okay, so what do we then know? Well, now we have to go back to the definition of big O and say, if this is true, what does that mean? What that means, by definition, n naught greater than 0, T of n is upper bounded by this purported constant. Sorry. It should be end of the k is upper bounded by this purported multiple of n to the k minus 1 for all sufficient. Okay, all I've done is invoked what it means to be big O of something else. All right, that's the definition here. Now we have to derive something obviously false. That's not hard to do. Let's just cancel the n to the k minus 1 from both sides. For all n at least n naught. Okay, see some number like 1,000,000. And clearly it is not the case that every natural number ever is at most 1,000,000, or at most this constant c. Okay, so this is obviously false. And that completes the contradiction. If you prefer, this shows that there's no winning strategy. Okay, there's no winning choice of C and N naught. Why? Your opponent, whatever you choose, can always then subsequently pick N bigger than C plus 1, and it wins. Okay, so your adversary will always win. It looks what you choose. It picks its N to be bigger than C plus 1. Okay? And then it flips the inequality. All right? So those are the examples. Any questions? Excuse me? Explain which? It's a number. Okay, it's some fixed arbitrary number. It's like 1,000,000. But what that thing is trying to assert is that every single integer, every single natural number is at most 1,000,000. But in particular, 1,000,001 is not bigger than 1,000,000. Okay, and that's true no matter what. That's clearly true no matter what C is. Okay, there is a natural number bigger than C, namely C plus. Okay, so this is a false statement. Okay? And from that, we deduce that our original hypothesis that end of decay is big O of n to the k minus 1, a false statement. We wanted to prove. Other questions?
In terms of completeness of the proof, how explicit or how carefully are we expected to be handling certain things like making everything be an absolute value automatically, makes it at least as large, that sort of thing?
I mean, it would be nice to have a half sentence. Say. I mean, ultimately, to be honest, ultimately what happens is you get graded based on whether or not you've convinced the TAs that you know what you're talking about, in effect. And so that's a pretty nebulous thing to define. I feel like the best I can do is give you lots of very concrete examples, which at least until you get more comfortable with the expectations, you can basically follow relatively closely. That's also one of the reasons I start out with divide and conquer. It has one of the more it's more cookie cutter than most of the other algorithm design paradigms. So more than other parts of the class, you should really kind of look at examples, say this is what's expected. Obviously it won't work exactly for your problem, but take away sort of the spirit of the level of rigor in the examples and try to apply that to your own solutions. And again, usually the first few weeks there's a little back and forth. You might overwrite your solutions, and then the TAs, if it's not wrong, the TAs won't take points off, but they might make a comment like, "Don't bother explaining this so carefully next time," or you might underwrite your solutions, in which case we might take some points off, but then hopefully you'll pick up and read the comments on your homework, and for the next time you'll know the appropriate level. Okay? So for now, I'm doing my best. I'm giving you as many examples as I can, but it is, the first few weeks, it's always some trial and error as far as what level of rigor we're asking for.